All right, so now that you have your typical neuron, what we're going to see is we're going to focus just on the axon. So I gave you a nice picture of the axon so that you could follow along and you don't have to draw it and I don't have to draw it out. So this is our axon. And you can draw your myelin sheath if you want to, but I'm not going to draw my myelin sheath on here. I'm just going to say that this is an unmyelinated axon to make our lives a little easier. And we're going to color code a couple of things. So we're going to make our sodium in red, excuse me, and we're going to make our potassium in blue to follow along with our lecture. And then I'm going to just make a little key for all the things that I'm going to put in the membrane. So you don't have to label each one. We're going to have a sodium potassium pump along our membrane. And I'm just going to make my sodium potassium pump look like this, half sodium and half potassium. I'm going to have sodium voltage gated channels. And I forgot to write sodium potassium pump here, Na plus, K plus pump. And then I'm also going to have a potassium voltage gated channel, which is going to go in that direction. So we're going to set up resting membrane potential. Remember, I already told you that during resting membrane potential, inside of the cell is going to be negatively charged. So inside the membrane, here we have a negative charge. And outside, we're going to have a positive charge, okay? In order to do this, we have to create what's called an electrochemical gradient. So electrical because you have opposite sides of electricity, or really you have opposite charges across your membrane. Inside is negative and outside is positive. The chemical part is the fact that you have different concentrations of ions on different sides of your membrane, okay? And I'm only going to draw on the top membrane, but this will be happening at the bottom membrane as well. This should be three-dimensional, so you'll have to think about it in a three-dimensional sense. And I might erase a couple of these because I need a couple sodium potassium pumps, maybe. So we're going to put our sodium potassium pump along here. And I'm just going to draw a few just so you don't think that there's like one sodium potassium pump. The sodium potassium pump will be all along the membrane. I'm just going to focus on one, but they're all going to be doing this simultaneously, okay? So first off, let's just draw our sodium potassium pumps in. What we're going to see is that during resting membrane potential, we're going to have a lot more sodium that's going to be placed on the outside of our membrane in the interstitial space, so the outside space of the cell. You'll have some sodium also, of course, inside the cell, but this is going to create a concentration gradient where we have a high amount of sodium outside, so high sodium concentration outside, and a lower sodium concentration inside. We're also going to have potassium. Okay, so potassium is going to be found inside of the cell at a higher concentration than the amount of potassium that's found outside the cell. And that's going to mean we have a higher potassium concentration inside. But you should notice that I have much more sodium outside than I do sodium and potassium on the inside. That's on purpose. Because along with the sodium and the potassium that I have on the inside, I have negatively charged molecules that are very large and can be very small. The reason why this remains negative on the inside is these very large negatively charged molecules, when they try to go to the membrane, they bounce off the membrane and they come back inside of the cell. So they remain inside of the cell. But normal cellular processes, so thinking back to basic bio from high school, or if you took a gen bio class here, what normal cell processes tell us is that when you have a concentration gradient, so an area of high and an area of low concentration, essentially what happens is that we have diffusion. So because we have a high amount of sodium outside the cell and a low amount of sodium inside the cell, naturally these sodium molecules want to diffuse inward. Okay, they also want to diffuse inward because they're positively charged and the inside is negatively charged. So the positive charges are going to actually attract to the negative charges. Okay, so we'll like maybe put 3 sodiums coming in like that. Because we have a gradient of potassium, so we have higher potassium on the inside than we do on the outside. And if I don't have enough potassium, I'll make one more. What natural cell processes tell us is that potassium is going to want to start to diffuse out of the cell. And this diffusion into the cell and out of the cell is going to be with our leak channels that we're just not going to draw here because it's easier to just say that it diffuses back and forth across the membrane. The problem with this is over time, what would end up happening is many of these sodium ions are going to diffuse into the cell and you would end up having the same amount of sodium inside and the same amount of sodium outside. And then the potassium would be the same. So potassium would diffuse out and you would end up having the same number of potassium inside and outside. And over time, this is pretty much going to make your electrical charge 0. And even if your electrical charge is not 0, you don't have a concentration gradient, which is what we need because we need to send a positive electrical message down our cell. So not only do we need to be negative on the inside, we have to have enough positive charges on the outside here in order to bring them in to depolarize our cell. So in order to prevent or counteract the diffusion of sodium and potassium, we are going to use the sodium potassium pump and energy. Okay. So this is a pump because it's going to go against the concentration gradient. Diffusion is a natural process that doesn't require energy. But if I'm going to pump against nature, so I'm going to do something against nature, I'm going to have to push energy into it. So our energy here, our ATP, will bind to each one of our sodium potassium pumps. And when it does that, the sodium potassium pump will take like these 3. So we'll erase these, this one, and this one. These 3 sodiums that just came in. And what they're going to do is it's going to pump 1, 2, 3 sodiums out. So then we counteracted the diffusion that we just did. And then at the same time, the potassium pump is going to take 1, 2 of the sodiums that diffused out. So right here, and it's going to pump them into the cell like that so that we counteract the 2 that just diffused out. So this helps us maintain the high concentration outside of sodium and the high concentration of potassium inside of our cell. And this is why our cell remains polarized. Okay, polarized meaning we have inside is negative and outside is positive. So as we finish this up, let's put this on our electrical chart right here. So we're going to start by making this millivolts, and this is going to be time, like that. So we're going to look at the electrical charge inside of the cell. So millivolts inside cell over time. At rest, we're going to see that we're a negative 70 millivolts. So this is going to be resting membrane potential right there. So in our chart, maybe pause the video here and see if you can fill out the chart on your own. Hopefully you paused it and you came back. Okay, so we want to think about at resting membrane potential, we're negative 70 millivolts inside of our cell. And here it's going to ask us, I'm going to move my picture over. It's going to ask us, where is sodium concentration high? Well, sodium concentration is high outside the cell. So you can say outside. Where is potassium concentration high? Inside the cell. Calcium, we're not worried about calcium for right now because we're not dealing with calcium. In order to maintain this, what membrane channel are we using? The sodium, potassium pump. And here we can say 3 sodium are moved outside and 2 potassium are moved inside. Okay, so perfect. We filled out all those things. So the next thing we're going to do is we're going to look at what happens if we actually stimulate our neuron.